Hi everyone, my name is Brody and I've picked topic 5 involving the atom and the periodic table, but focusing on representative elements and their valence electrons. I will be showing you Lewis dot structures and recognizing trends on the periodic table. So I would like to start with the root of this topic, which is the periodic table and where the representative elements are. There are 8 groups of representative elements on the periodic table, and they all have an A in their group label. I have circled the group labels on all of them so you can see. The group label is located under their group or column number. So the group 1, their group label is 1A, group 2, their group label is 2A, etc. The noble gases, which is in group 18, but their group label is 8A, are included in the representative elements. The representative elements consist of metals, metalloids, and nonmetals, and I have screenshotted this from our course, and I have thought it was very helpful in showing me where the metals, the nonmetals, and the metalloids are located on the periodic table, so I thought that was a handy. So as we know, valence electrons are the electrons in the outermost shell of an atom. The first shell consists of 2 electrons, followed by the rest of the shells, which can each hold 8. To find the valence electrons of an element, you take the element's atomic number, which is located above the element symbol. And you can see here that this is the element symbol, and this is the atomic number, but I have circled a few examples for you guys in red. So you distribute the atomic number, which is equal to the amount of electrons the element has, and you distribute them in the shells. So for example, I'm going to take the representative element oxygen, and we're going to find its valence electrons. So as you can see, oxygen's atomic number is 8, meaning that there are 8 electrons. And we're going to distribute them throughout the shells. So the first shell holds 2. So I'm going to do 2 electrons. Okay, and so that leaves us with 6. And the second shell can hold up to 8, so that means all 6 can go in the second shell. So I know my drawing is not perfect, but in real life, they're not circles anyway, so it's okay. So 6. So that means that oxygen has 6 valence electrons because it has 6 electrons in its outermost shell. So that equals 6. I'm going to do another example with nitrogen, which has 7 total electrons. So it has 2 in the first shell, and then 3, 4, 5, 6, 7. So nitrogen has 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons because it has 5 electrons in its outermost shell. Now that we get the hang of it, I'm going to fast forward and find all the representative elements' valence electrons for you. Okay, so I've found all of the valence electrons for each representative element, and I've written them next to the elements just in blue on the periodic table for you guys. So now that we know the number of valence electrons for each element, I'm going to show you how to write them in a Lewis dot structure. So the first step is to take the element that you are doing it for. So I'm going to take the representative element boron, which is in period 2 in group 13, and the group label for boron is 3A. And boron has 3 valence electrons. So the first step is to write the element symbol. So for boron, it is just a B, and you can see on the periodic table that the element symbol is just located right under the atomic number. So the second step is to take the number of valence electrons that your element that you're working with has and write it and distribute them in a dot form around the element symbol. So the finished Lewis dot structure for boron would look like this. Now, when writing the dots, you have to follow a certain order. So the first dot would be above the element symbol at the top, then the second dot would be at the bottom, then the third dot to the left, and if boron were to have a fourth valence electron, it would go to the right, and then back up to the top, and then clockwise around. So I'm going to do this again, but this time I've picked an element that I know has 8 valence electrons, so it will be a full Lewis dot diagram with all of the dots, just so you can see how I do it. So argon's element symbol is Ar, and it has 8 valence electrons. So we're going to go to the top, the bottom, the left, the right, back up to the top for the fifth, and then we're going to go around clockwise until it looks like that. And that will show 8 valence electrons around the element. I have done a few more dot structures for more representative elements with different valence electrons, so you can see what they look like as well. I've just included the element's name and then the number of valence electrons that the element has, and then the Lewis dot structure for it just right beside it. Okay, so the last thing that I'm going to be talking about is trends on the periodic table. I'm going to be starting with the atomic radius. The atomic radius is the size of an atom. So if you were to start at the top of the periodic table and go towards the bottom, the atomic radius would increase, and that just means that the size of the atom would get larger. Now, if you were to start at the left of the periodic table and go towards the right, the atomic radius would actually decrease. And that's because even though these atoms have similar shells, the atoms towards the right of the periodic table have more electrons. And those electrons are attracted to the proton in the nucleus, which makes the attractive forces in that atom stronger than those towards the left and makes the atoms shrink. So I'm going to draw an arrow this way just to point out that the atomic radius is higher towards the left side. As you can probably assume, the atoms in this corner have the highest atomic radius on the periodic table. So the last trend that I'm going to describe is ionization energy. Ionization energy is the amount of energy needed to steal a valence electron away from the outermost shell. So as you move from left to right on the periodic table, the ionization energy increases. And that just means that the atoms closer to the right side of the periodic table is harder to steal their valence electrons, and that's because, like I said earlier, their attractive forces are so strong. Now, if you go from the top to the bottom of the periodic table, the ionization energy actually decreases. So I'm going to draw an arrow this way just to show that the ionization energy in the top right corner is the strongest. And that just means that it is hardest to steal electrons from this corner. Now, the easiest place to steal electrons, as you can probably guess, is this corner. And that's because since these atoms have the biggest atomic radius, they're the largest. And that means they have so many shells. And so these shells are so spread out from the nucleus that the attractive forces are weak. And the weakness makes it the easiest place to steal electrons. So that's one overall trend we can recognize, is that places where the atomic radius are the largest is the easiest place it's going to be to steal an electron. Thank you for listening, and I hope you enjoyed, and I hope my little presentation helped someone out a little bit, and thanks for listening.